Okay, hello everyone. Welcome to the 6th session of the AI and ML in Medicine course. And today we have Dr. Nidhi Hegde from the Department of Computing Science. She's an associate professor in there, and she's also a fellow with the Alberta Machine Intelligence Institute, and she's a CFAR AI chair as well. We're pretty excited to hear about differential privacy today, and she's going to be giving us a short tutorial. I'm pretty excited about today's lecture. So without further ado, I will let her take it on from here.
So I'll let you. Sure. Okay. I hope you can all hear me okay. Yeah, okay. Well, I guess you can't tell me if you can't hear me. So maybe if you hear me, can you? Yeah, there we go. Okay. Okay, so my research is in machine learning, mostly focusing on privacy and fairness. So I was supposed to talk about privacy and fairness, but there's just not enough time in 1 hour to do both. So I'm just going to talk about privacy today. And I'm going to talk about privacy in general, and then at the end, I'll try to bring up some points that are specific to the healthcare domain. So, okay, so as we all know by now, we're sharing our data pretty much with everything we do today, in terms of what we're searching on the internet, our social network interactions, these genomics testings and so on. And of course, things that you purchase online. And sometimes data about you is collected when you don't even really know, like when you're using your cell phone. For some of the network operators, they need to know where you are. So there's that location data being collected for networking functionalities, but it's also actually used for other things. So there's data about you, and that device that you're using is also specific to you. So it's really about you, not just your phone. That's being collected everywhere, whether you want to or not. And a lot of this is actually used for some useful services for us, like recommendations that you might be looking for on streaming services like Netflix, or purchase platforms like Amazon and so on. Might be used for some predictive analysis, like in healthcare, might be used for predictive analysis, like how many beds need to be available at a certain for a certain scenario. Oops. So, there are a lot of, and actually even, I don't think this happens in Edmonton, but in a lot of cities in transit, where you have that tap on and tap off card, which we just started in Edmonton, that information is used also to determine, where the new transit lines should go, or which lines are busy and which should have more frequency and things like that. So there's a lot of stuff that's useful to us. But of course, there's a lot of private information in there also, and we don't want that private information revealed. And it's not just in terms of the information like, where you've been during the day, your location data, but you don't want that inadvertently being used by, say, the purchasing platform where you bought something, right? Like there's separate kinds of data about you that's being collected. And when put together, things can be inferred about you that you probably don't want inferred about yourself. So that brings us to the notion of privacy. But this idea of privacy is not really that well understood, in the sense that not everyone has the same idea of privacy. So if I were to ask you, what do you think is privacy when it comes to data, machine learning, AI? What would you tell me? What's privacy for you? Anyone? Without your consent. Okay. Okay, anyone else have an idea about what privacy is? Collection. Okay. Anyone else? One last one I'll ask. Anyone? For me, it's control over how my data is collected and used. Yeah, okay. Yeah, so that's generally the type of answers I get when I ask this. You want to control who sees your data. You want to decide what you want to share, who has access to your data. Your data is secure. Your data is something about you, nothing about you is known, or some personal information about you should be hidden, and so on. So when we talk about privacy and machine learning, there's a very specific notion that we're actually referring to. So a lot of these ideas that are up here refer to different things like security or anonymization or access control. So all these things on the left, like who sees my data, who can access my data, what data is accessible to people, I decide who can see what, things like that. That's really about access control, right? It's really about what data can be used about you, who can see it, and so on. And then on the other end, we have things about data security, whether your data is secure, whether it's encrypted, and so on. So privacy kind of lies in the middle. It's not necessarily about security, because once your data is decrypted, well, there's lots that can be learned about you from that data, right? So it's not really private. It's secure, but not private. And access control is, still allows whoever has access to be able to infer things. If there's certain types of data that you want to allow access to, even that can be used to infer things about you. And you'll see an example of that later on. Even things that you think are benign about you can in fact be used to infer other things about you. So privacy is really a notion in machine learning, which is maybe not very intuitive, but it's about not learning something new about you. And I'll get into that in a little bit more detail. So a lot of times people say that we can achieve privacy by anonymization. So you have data sets, data that's collected about you. Amazon has a particular data set about you. Netflix has a data about you in its data set, and so on. So people say, let's just do anonymization, where your information is in there, but your personally identifiable information is hidden, like your name is removed. And personally identifiable information is information that identifies you specifically. So that could be your name and date of birth, for example, right? That's a very unique to you. Name, date of birth, and address, maybe that's very unique to you. Your social insurance number, that's very unique to you. So these things are personally identifiable information. And anonymization is really about removing that personally identifiable information. And then that data is anonymized, so it should be fine. Your personal information is hidden because your name is not identified to that information. So generally people think this should be okay, and this is done very commonly. Anonymized data sets are shared all the time. But does that really guarantee privacy? And actually it doesn't. And there are a couple of really good examples, real life examples that show that it doesn't. So just by having a publicly available data set without information like name or specific address, it was shown that you could still uniquely identify people. And so this was from US Census summary data, not from this past census, but from the one before that, which I think was 2010. But even before that, so LaTanya Sweeney, a researcher in privacy, did this, I believe, in the late 1990s. And there she used US Census summary data, and she was able to show that only 3 features were sufficient, and those 3 were zip code, birth date, and gender, to uniquely or nearly uniquely identify 87% of the population. So your name, social insurance number, which are very specific to you, were not necessary. So just with this 3 pieces of information, you could uniquely identify. And if you just do some back of the envelope calculations, this makes sense. So for example, birth dates, there's 365 days in a year. Let's say there's like 100 different ages that we will consider. There's 5-digit zip code in the US, and in that census data, there were 2 genders. And so that's about 365,000 combinations. So the zip code is specific to, a certain geographical area, county or something. And if you look at these geographical areas, in most of these counties and zip code areas in the US, there's a lot fewer than 365,000 residents. So, you could, very easily try to identify people by just using those 2 remaining things, which are birth date and gender. Okay, so this is just census summary data. It's supposed to be public anyway. You can't really learn much about a person, big deal. But there are cases where there's sensitive information that was used to uniquely identify people. And this re-identification was done because it's not just your personally identifiable information that identifies you. It's really any information about you that distinguishes you from some other person, right? And so knowing that, you could easily link a person's information, like a set of information about somebody, you could easily link that to someone by using a different data set. So one example was over 20 years ago in Massachusetts. So in the US, the healthcare system is very different. You have insurance markets, and things are, there's actually a market for, healthcare data in the US. And this is at the state level. So at the state level, there is collection of hospitalization data. And some states, publish this data in an anonymized version for the insurance market and so on. So this particular case study is that in Massachusetts, the governor in Massachusetts at the time, this was in the late 90s, early 2000s, wanted to improve the insurance market or improve the competition in the insurance market. So he wanted to publish anonymized hospitalization data. And since this was the state government, they had control over the hospitalization data of the state employees. So he wanted to release the anonymized version of that so that, analysis can be done on it to improve the insurance market. And on the same side, in the US, you can buy voter registration data. And this is, sort of demographic data about people, like where they live, their zip codes, their birth dates, and so on. So, and in releasing this anonymized data, the governor said, don't worry about it. The data is anonymized. Nobody will know who you are in this data set. So again, LaTanya Sweeney, who was, I believe, working in Harvard at the time, said, well, let me show you. You could buy voter registration data for $20. She did that, and she was able to link the anonymized private data set with this public voter registration data and re-identify people. And in particular, she re-identified the governor himself. And turns out that he had cancer that he hadn't told anybody about. And that particular case was very easy because in the Cambridge, in the area that he was living in, there were only 6 people with the same birth date. Only 3 of them were male, and there was only 1 in that particular zip code. So it was very easy for her to identify who he was in that anonymized data set. So this was a very neat gotcha moment. But people say that, maybe birth date, gender, these should be considered as personally identifiable information, because this is, if you put 2 or 3 of them together, obviously it will personally identify you. There's not a lot of people who may have that same combination. And so this idea of PII is actually very different depending on where you live. In Canada, which goes by the PIPEDA Privacy Act. In the EU, we have the GDPR, which is their privacy directive. And in the US, it's a bit of a chaotic situation. There's different agencies that have different laws and rules about privacy, and they all have their own definition of what PII is. So it's really not easy to have sort of a unified understanding of what anonymization might be. But actually, even if you consider the largest set of PII and you remove that from a data set, you are still able to re-identify people. And this was shown in a very interesting case, I guess 15 years ago now, 12 years ago, I don't know. The years get smaller as I get older, so I don't know. But this was a particular case of Netflix. It's called a Netflix competition case study. You may have heard about it. So in 2006, okay, so that was quite a while ago, Netflix had this competition where they have this they had at the time a recommendation algorithm, which had, so I don't know if you are old enough to have had Netflix back then in 2006, but I am, and they used to have this star system. When you saw a movie, there was like 1 to 5 stars that you could give it. Now it's just thumbs up, thumbs down. I think there's like a double thumbs up even, I don't know. But anyway, so they had the star system. And so they use that information, the rating that you gave a movie, to then recommend other movies to you. So their competition was, if you could improve their recommendation algorithm by 10%, meaning the accuracy of that algorithm. So if you were to, accuracy meaning that if the algorithm recommends something to you and you do like it and watch it, that's a good hit. So if you came up with a recommendation algorithm that improved their performance by 10%, then you win $1 million. So lots of groups and teams signed up for this. And just as a side note, they actually never ended up using the winning algorithm because it was too complicated. It was just like too many things that were clumped together. And they actually don't even have that 5-point rating system anymore. Okay, so what did they provide people with for this competition? So they released this anonymized data set, which was a data set of 100 million movie ratings. So it contained information, rating information from about 480,000 subscribers, 17,000 movies. And each row or each set of data points essentially had user, movie, rating, data rating. And the user was actually nothing related to the user at all. It was just an anonymized random 5-digit string for a user. And then it had the movie that they rated, the rating they had for the movie, and the date of that rating. And that's it. So just 2 weeks after that data set was released, there were some researchers from UT Austin that linked this data with public IMDb data, and they were able to re-identify several people. And that's the paper, if you're interested, that does that. So what they did basically was that they looked for similar patterns in the 2 data set, right? So it didn't matter what the user random digit was. All they were looking was for the pattern, the movie, the rating, and the data rating. And they tried to see, you have many movies, right, for a single user. Not all users watched all those movies, but you had sufficiently enough movies that you could take that pattern and try to find a similar pattern in the IMDb data. The IMDb data, of course, doesn't have true identification. It just has a username that the person has chosen themselves and any other information that they choose to put up there on their own. So basically, it was very simple. The IMDb data set is called auxiliary information or sort of supplemental information. And basically, they took a row from that. They took a row from the Netflix data set and had a score of the similarity. And they used different similarity metrics. In general, if you have 2 vectors, you could look at similarity by looking at the distance between the 2 vectors, and there's different ways of calculating the distance. So they had a few different ways of calculating that distance. And essentially, they said that 2 rows were a match if the score was over a certain threshold. And they kind of heuristically decided on a threshold, but that was good enough for them to identify people. In fact, what happened is that when they identified certain individuals, this was a privacy breach, not only because it was identity disclosure, but it also disclosed behaviors that this person had on IMDb that they didn't necessarily have on Netflix. And this one particular instance, the sexuality of a person was revealed by connecting their Netflix data with the IMDb data set. And so this person, we don't know who it is called her, she's called Jane Doe, sued Netflix because this information about her was revealed only by using her username in IMDb, but her friends and family knew her username, so they were able to learn this information about her sexuality that she had kept hidden from her own family. So she sued Netflix. We don't really know what happened because they ended up having an agreement. And then Netflix had another competition, which they then canceled because they probably couldn't afford more lawsuits. So essentially, this says that releasing any kind of data set, whether you've anonymized it or not, as long as it contains certain patterns that are relevant to users, that can be still used to re-identify individuals. And that's because it's really that pattern of your data that identifies you specifically. So in what kind of instances does anonymization not work then? It doesn't work when there's data about you at multiple sites. So this could be different types of data about you. There might be some overlap, there might not be. It might, if you can think of a person as sort of like a multidimensional object, some data sets will have this side of you, another data set will have another side, and you could probably infer things about the person when you combine them together. Another case where anonymized data is susceptible for re-identification is when you have high dimensional data. And this intuitively makes sense because high dimensional data means that you have more features in that data set. And so the more features you have per user, there's a higher risk because it's more likely that a particular pattern is unique, right? So if there's only 2 features about somebody, there's only so many combinations, but if you've got 10,000 features, it's very likely easier to uniquely identify you. So if anonymization, any kind of anonymization doesn't work, then how can we, protect private information and yet still be able to do some valuable analysis from the data? Well, one idea is, okay, let's just not even release any data. We're not going to release any data sets, but we'll allow some aggregate queries, like maybe some statistical queries, like what's the average age of people in this company, or what's the average salary, what's the median height, whatever, something like that. Or you could even have something complex like a machine learning model, and we're only going to release the parameters of that model. Or even, let's be even more careful, we'll have a black box thing. We'll only allow people to submit inputs and we'll only give them outputs. That should certainly be private. Well, it turns out even that is not really sufficient. So if we're just talking about aggregate queries, you can have reconstruction attacks. And this was shown for a few cases. This was people from the US Census Bureau actually that showed it, because a lot of times US Census Bureau releases summary data like statistics, like averages, medians, and so on. And they showed that if you're releasing sufficient number of statistics, then people can very easily write this as a system of equations and then be able to reconstruct the original data table. And that's just a satisfiability problem. And even if you have a large data set, there's different kinds of statistics that you're collecting. There's lots of SAT solvers out there that can solve these systems of equations for you. So you can reconstruct the data set. Maybe you don't reconstruct it completely, but maybe you don't need to. Maybe just even this partial reconstruction is sufficient for a privacy breach. And then you have something called membership inference attacks. And this is what happens when you have machine learning models that are released. So you're saying nothing about the data, you're just releasing the model parameters, or even just a black box model where you only allow inputs and outputs. And this membership inference attack is when someone is able to infer whether a data about a particular individual that they know was used in the training or not. And that's important because if their data was used in the training, then they know that this output of the machine learning model is somehow skewed in their direction, right? So they can infer things about that person with that supplemental information that they know. And so we need something a little bit more robust to guarantee privacy. And this idea of membership inference attack is really what bothered a lot of privacy researchers. Like, how do we make sure that this is what's protected, like that someone's data was used in the training of the data? That idea actually comes from a more general idea of privacy, where an attacker who may have some background information about an individual should not be able to learn something more about that individual if they have access to this new machine learning model or data set. And that's what a statistician from many years ago claimed is a reasonable notion of privacy a lot of researchers have come to accept. And he says that if the release of a particular statistics S makes it possible to determine some private information about an individual more accurately than was possible without access to that S information, then a disclosure has taken place. So he's basically saying that anybody with some information about a person shouldn't know anything more than that if they have access to some data or a model about that person. So privacy means that you can't learn something about an individual. You can't learn anything more about an individual if you have access to that data. So that essentially is another way of saying that an adversary's prior and posterior information should be similar. And this is what led to this definition of differential privacy, which is pretty much the standard that's accepted by machine learning researchers today. And what it says is that, let's say I have this one data set and it has this one person in it among many others, and you have some query on that data set, whether this is some kind of a statistical query or it's a machine learning model that's trained on that data set and then is having some output, you get some kind of outcome A prime. And then let's say you replace that one person in that data set with another person. And this could be any given individual in that data set, and you do the same query again and you get some other outcome A. So what differential privacy says is that these two outcomes A and A prime should be very close to each other. If they're very close to each other, that means that you're not able to tell if it was this woman or this man in a data set, and therefore you don't know whether someone participated in that analysis. And that means that this process is this query mechanism or this data set is differentially private. And the way you would achieve that is by randomization. And the reason you achieve that by randomization is because essentially what you want is some kind of randomization that makes these two outcomes similar, okay? And this idea of randomization is not anything new. In fact, social scientists, economists have been collecting a lot of sensitive data about people for decades now, right? Like since the middle of the century. And they do this by surveys, like individual surveys and interviews of people. And they had adopted a mechanism of making sure that the data that they're collecting was private. So they would have sensitive information, maybe like, did you cheat on your taxes or whatever? And there was a particular protocol by which the respondents would answer. And this was a randomized response protocol. There's many different types, but this particular one is a very simple one to understand. So they told the respondents, flip a coin. And if it's tails, then answer truthfully. Like if this is a question with a binary answer, did you cheat on your taxes, yes or no? If it's heads, then flip another coin. And if that second coin is heads, you respond yes, regardless of what your true answer is. And if it's tails, you respond no, regardless of what your true answer is. So now your answer is now randomized, right? So the person who is listening to your answer doesn't see how many coins you flipped or whether it was heads or tails or anything. All they see is your answer. So just by looking at your answer, they don't know if you said yes because that was the truth, or if you said yes because you flipped the coin twice and you got yes. So this protects the individual respondent because a particular answer is not incriminating. You don't know whether it's the truth or not, but they are still able to get aggregate statistics. They're still able to estimate the population level information, right? And you can do this. This is a very simple calculation. If P is the true fraction of cheaters, and that's what they're trying to estimate, and then the number of yeses that they expect is essentially a quarter plus P over 2. And this is a very simple calculation because the probability of having tails in this first instance here is a half, and you're saying yes if with a probability of P because your true answer was yes. And then you get heads and then you flip a coin again, that's a probability of a quarter. And then that's what you're saying yes with, right? So you can very easily estimate what the true proportion is without knowing what the true answer of each specific individual is. So this is a very nice randomized method. And that's kind of what we want for general machine learning models. So this is for binary queries, right? Queries with binary responses is very limited. So we want a similar kind of a randomized mechanism. I'm going to call it M, that operates on your data set. And when it operates on the data set, when you change one individual and replace them with another, the output should be close. So have randomization in M, and what close means is that because you have randomization, your outputs are now distributions rather than some specific deterministic values, right? And so close means that these distributions should be close in the sense that over the entire support of these distributions, there's a bounded ratio between the two distributions. And that basically leads to the formal definition of differential privacy, which says that the probability, so this mechanism M, this randomized mechanism, is differentially private if the probability that you get a certain output O when your input is data set D, and the probability that you get that same output O when your input is D prime, where D prime is just the same data set, but you've changed one user in there. The ratio of those two probabilities is bounded by exponential to the epsilon. And pictorially, what that looks like is if orange is the distribution of the outputs when your data set is D, and blue is the distribution of outputs when your data set is D prime, then these distributions should be very close, meaning that they have a bounded ratio. There's some interesting mathematical explanations for why this is a ratio and not a difference, but I'll leave that for now. And I'll just say that when you're looking at this, essentially this value epsilon is the parameter that sort of measures or is an indicator of how much privacy you have. So the closer these two distributions are, that means epsilon is very small. The closer these two distributions, the smaller epsilon, and the more privacy because you're not able to tell the two distributions apart, right? Okay, so that's the formal definition of differential privacy. Now, this can be a little bit restrictive because if you want to ensure this bound over the entire support of the distribution, that can be a little restrictive because you may have certain cases where one output has a probability that's very different. And if you try to ensure that everywhere, you might end up with a very loose bound. And so there is an approximate version of differential privacy where you have this additive element here. But in essence, it's really the same thing. It just says that the output distribution should be very similar. Okay, and this is very nice because it has some really nice properties that can be useful for machine learning analysis, analysis of machine learning models. And one nice property is that it's invariant to post-processing, meaning that if you have some data set that you then use to create a model that's differentially private, you can do any kind of other processing on it after that, on that output after it's been differentially private, and you don't lose the differential privacy. You still retain that same level of privacy. You can't turn it back. You can't reverse engineer the privacy, essentially is what this says. And then you also have this notion of graceful composition, which means that if you have multiple functions that you're performing on this data set, you can combine them. And if each one of them is differentially private, then the combination is also differentially private with the parameters that sum accordingly. Okay, and these are actually interesting properties because this is really what happens in true deployments and implementations is, you learn something about a data set, you use that to do some other analysis and so on. And then another one which is useful is group privacy. Maybe you're not interested in protecting one particular person, but maybe a group of people, and that is also easily doable in this framework. Okay, that's nice, but how do we actually achieve this? Well, we already looked at one example, which was randomized response on the binary answers. And if you actually do the calculation of, what the probability of the output is for a given data set, and then for a neighboring data set, then you end up with a ratio, which is 3, which means that this particular mechanism is log 3 differentially private. Okay, what does that mean? It's log 3 differentially private. Obviously, these things are understandable only in relative senses. So a smaller epsilon is more private than a larger epsilon. That's something we can say. But intuitively, what does that mean? People have done experiments in terms of privacy attacks on models that have been protected. And from that, they've learned that a reasonable level of privacy is given when you have an epsilon between 0 and 10. And this is interesting because a lot of current mechanisms that people claim are differentially private, like for example, Apple says that it has differential privacy in the way that it collects statistics from MacBooks, from their devices. They're constantly collecting statistics, right, about what you're actually doing, or how things shut down, things like that. So they claim that they're using differential privacy in how they collect that data. Google claims that they're using differential privacy in how they collect data from the Chrome browser. But it all goes into what actual parameter that they're using. And Apple is using something beyond 10, and so is Google. So it's kind of meaningless. They're saying they're using differential privacy, but that parameter is so large that, meaning that, these two distributions are so far apart that, it's not really privacy. Google is an interesting example because they're actually using randomized response, but in a very interesting and complicated way. Okay. They probably could use a better value of epsilon and get away with it because they have access to so many different samples, but they don't. They use a really irrelevant value. Okay, so how do we actually achieve differential privacy when you don't have binary answers? So the idea with the randomized response was that you want to add some noise, you want to add some perturbation, and that's what is guaranteeing the privacy. But we want noise that depends on the query, right? Like that randomized response was a binary query. You would add noise differently if it was a query which had a range from 0 to 100 than if it only had 2 possible choices, right? So the noise should depend on the query. It should be symmetric. If you're adding if you're adding noise too much on one side, obviously, a smart observer can figure things out. And you want it, you want it to depend on the actual query. And so the method that was proposed a few years ago and that's still popular now is called the global sensitivity method. And in this particular case, I'll show it for only statistical queries on databases. And again, the differential privacy notion is that your output shouldn't change by too much when you change your input by one individual, right? So obviously, if that's the definition of differential privacy, then the noise should be somehow calibrated to how much your output might change. And that's the sensitivity. So the sensitivity of a particular query is how much the output of that query changes when you change the input, in the worst case, by one person or one data point. This global sensitivity then, once you calculated that for a particular query, that's what's used to then determine how much noise to add. So the sensitivity is the upper bound on how much the output changes and therefore how much noise we should add. And the noise should obviously be a random variable. We want to add random noise. We don't want to add deterministic noise. Okay, this is just very specific here. And just to give a couple of examples of what the sensitivity looks like, if you have a query which is, let's say, the mean, like you want to know the mean age, for example, in a data set, or a mean of some other feature, then your sensitivity is how much that mean would change by in the worst case. So if, for example, you had a feature which had values between 0 and 1, and you wanted to find the mean of that feature in a data set, then the sensitivity is 1 over n, because the most that the mean would change by if you were to replace a data point is 1 over n, right? 1 is the largest value that feature could have, and you have n. I didn't mention that, sorry, you have, well, I sort of mentioned it implicitly up here, but you have n values in your data set. So if you had like a count query, which is a very simple query, like I don't know how many people have blue eyes in this data set, something like that, then your sensitivity is 1, because the most you could ever change by is 1 when you replace a person in your data set. Another common query is a histogram query. This one, the calculation of the sensitivity is a little bit tricky because it depends on how you define this data set D and D prime. If you're replacing a user but keeping the size of the data set the same, then the sensitivity is 2, because the person that you're adding might go to a different category, and so you're reducing by 1 and adding by 1, so that's 2. But if you're changing the data set by just removing a person or by just adding a person, then the sensitivity is 1. So the way you use this sensitivity is it's going to be a parameter in how you add noise. So you want to add random noise. And in the simplest case, and it turns out this is pretty much an optimal way of adding noise, you would use a Laplace distribution. So let's say your true answer for this query, whatever this query is, F on this data set is FD. This is your true answer. The private answer, or the privatized answer that you would publish, is FD plus Z, and Z is a random noise which is drawn from a Laplace distribution, which is centered at 0 and has this shape parameter, the sensitivity and the privacy parameter. So just as a reminder of what a Laplace distribution looks like, it's essentially a double-sided exponential distribution. If the mean is 0, it's centered at 0, and the shape parameter, which is B here, this picture is from Wikipedia, essentially determines the shape. So if you're centered at 0, if your shape parameter is very small, then you have a peaky distribution, which means that you have high probability of picking smaller values close to 0, or you can have a more flatter distribution where you have a higher probability of picking larger values, right? So obviously this parameter then is important, and it would be calibrated to the query that you have. So the sensitivity then, the sensitivity value is part of that shape parameter. So the higher your sensitivity value, that means the more your answer changes, and so you want to add more noise. So the higher your sensitivity value, the flatter your curve, and so there's a higher probability of larger noises. And then same thing with the parameter epsilon. The smaller the parameter, you're adding more noise because the curve is flatter, and so you're being more private. So this is a very nice way of calibrating how much noise you add according to the level of privacy that you want and the sensitivity of that query that you're adding noise to. This is just an example for a very simple count query. You would just add Laplace noise with the shape parameter 1 over epsilon. Okay, and this is just a demonstration sketch of the proof to show that this Laplace mechanism does verify the definition of differential privacy, but I won't go into the details here, since that's probably not of main interest to you, the proofs. The other point is that you can also use the sensitivity method if you wanted to add noise according to the approximate differential privacy, and that one had 2 parameters, the epsilon and the delta. So instead of a Laplace distribution, you would then use a Gaussian, which is also centered at, which you can also center at 0 and is symmetric. The delta value basically changes the variance of the Gaussian distribution. You know, if you look at, I don't think I have a picture of that, but if you Gaussian distribution, you probably know what it looks like. It's a bell curve. If you compare that to the Laplace, it's kind of rounded at the top. And that essentially is what makes sure that you have that relaxation of that delta, so that the high noise, the high probability of the small noise values is what's not there in the approximate differential privacy. So if you're intuitive about these probabilistic notions, that might be useful for you to think about the difference between the two types of differential privacy. Okay, so these are, pretty much well-accepted notions of privacy. And there's various kind of scenarios where you can add perturbation. The initial case we looked at with randomized response was this scenario where you had each user had their own data. And when their data was collected is when it was sanitized. So this is where you added the privacy. So whatever data set that contained all of the data was already privatized. And then you had queries and responses there. A more common notion is when you have a centrally located data set of the users, and then you add a differential privacy mechanism to that data and get a sanitized data, and that's still input perturbation. But that, it turns out, ends up adding too much noise, and it makes your data very unreliable. So instead, what people do is you have a trusted curator that keeps the actual data, and it's the query responses or the outputs of the machine learning model that are made differentially private and then published. So it's the output perturbation scenario. Okay, so does this work in healthcare situations? Can we just take this and apply it to any kind of problem we have in medicine or healthcare? Not really. So a lot of healthcare privacy issues in healthcare are about data sharing. So it's about, rather than it's sharing of the outputs, it's really more about sharing of the actual data sets. And in this case, differential privacy can be quite unsuitable, and it can even give you very wrong results in some particular scenarios. And those scenarios are, for instance, where you're using the, when you have a method that's predicting like dosing, so personalized tools, personalized machine learning tools in healthcare are not suitable for differential privacy. And there was one particular study done where they looked at dosing of the drug warfarin, the blood thinner, and they found that adding differential privacy, even if it was, small amounts of noise, gave very unreliable dosing predictions. And so you can imagine, if you were to use that for actual warfarin dosing, you could put a lot of lives at risk. So you have to be very careful what kind of scenario you're using it for. Like general population level diagnostics, that's doable with differential privacy, because that's the goal. You want to hide private information, personal information, but at the population level, you're still okay. But for personalized tools where you're doing some dosing or something very specific to a person's care, these are the scenarios where differential privacy is not reliable. So data sharing is very popular in healthcare, and we need that for research, for development of diagnostic tools, and so on. So if we're, obviously anonymization is not suitable, but if we can't really do differential privacy, then what else can be done? So there's a couple of things that we've been looking at recently, and that is, can we at least identify the privacy risk of sharing a particular data set? And maybe then the decision makers can decide if this risk is worth it for sharing that particular data set. So this is some preliminary work we've been doing with some people in AHS, and that is identifying, identifying a heuristic or an algorithm that will output a privacy risk value for a certain data set that you want to share. And so far what we found is that for the exact same data set and the same task, so maybe you have a classification task or a regression task, and you have the exact same data set, but you have many different models that you can use, right? For example, you can use a random forest, you can use decision trees, you can use logistic regression for that same classification task. And it turns out that if you have no differential privacy, you're just, training these models as they are, they offer different levels of privacy as it's measured according to that membership inference attack that I talked about earlier. So different models naturally have different levels of privacy. That maybe goes into the policy decisions, like you need to specify exactly what you're using the data set for sharing. And maybe you can only share certain portions of data. So with this particular scenario, we've been doing some experiments on if we share maybe all rows of the data set, but only certain features. Or if your data set has multiple classes, so the label, the target variable in your data set has multiple classes, it's not just binary. It turns out that the more that number of classes that it has, it directly impacts the level of privacy in terms of the susceptibility to attacks. So maybe you can lump certain classes together and have only 2 classes or something like this. So these are the things that we've been experimenting with so recently, is how can we change the view of the data set that we're sharing in order to reduce the privacy risk. And this actually leads to a more fundamental theory problem in data sharing, which is that if you have a very high dimensional data set, it turns out that if you just take a random projection of that data set, and by random projection, a projection of a data set means that you're taking that high dimensional data and you're projecting it to a lower dimension. And if that projection that you're taking is just some random projection, like if you're comfortable with linear algebra, this could just be a JL transform or something, then that actually is sufficient to ensure privacy. It turns out that just taking a random projection may satisfy differential privacy. So then the problem that we're looking at now from a fundamental theory level is, can we have successive random projections of the same data set that each ensure differential privacy, and you can't combine them together to gain something else? So there are a lot of interesting fundamental theory, foundational questions that we've been asking about how to do private data sharing, especially when it comes to healthcare kind of data. So I'm going to stop here. And this just basically lists a few open questions that we have right now in this area of privacy. I went a little too long, sorry about that, but if you have questions, I'm happy to answer or discuss something. Anybody in the chat? No. Okay. Was that too dry? Was that not? Okay. Well, this was a lot of information with going over the different ways of looking at privacy. So it might take you some time to think through it all.
More so like in the discussion sort of thing. I think, especially with Connect Care coming in Alberta and like our electronic medical system changing a little bit as well, there's a huge potential for a lot of like bigger machine learning algorithms to be trained through this. Do you know if like AHS has any sort of collaborations, at least with CS, to kind of look into that, and if there are any sort of data sharing protocols that are being developed for it?
I wouldn't say there are like specific protocols being developed right now. AHS as a whole hasn't reached out to CS researchers, I guess, to look into this. There's specific groups or people that are interested in this, like the person in AHS that I've been discussing with, who, well, anyway, they're responsible for a certain type of data in AHS. Maybe I shouldn't say what kind of data, I don't know. But in general, this kind of information, and AHS specifically, is very strict about data sharing, and they err on the side of not sharing at all, rather than allowing for a little bit of has a little bit of uncertainty. And that is a complaint of many researchers because even people who work within AHS don't have sometimes access to the data because of these very restrictive privacy. So I'm hoping that eventually they will learn about more privacy preserving methods so that that allows them to share the data rather than have this secure access control method where they just don't want to share the data at all. But one of these things that we're working on is trying to calculate the privacy risk. At least that gives them some tool in their decision making. Like it could be a heuristic, like if the privacy risk is above a certain value, we don't want to share it, right? That could be a very heuristic type of decision like that, but it's at least partway to an optimal solution. And in terms of Connect Care specifically, so there's a lot of hesitancy because one nice thing would be for doctors who are treating, like maybe even family doctors who are in consultation with a patient, they're treating a patient, there's a bunch of symptoms, and maybe they want to look in the data set in the Y database to see, well, what do other patients who have similar symptoms look like, and what has happened to them, right? That's a thing that you want to know because this might be similar. That's not allowed according to the current access control rules, but it's very useful data. So, there are solutions to this. There are ways of presenting that data to the doctor without having a privacy leakage. But I don't know if they're looking into that right now or not. That's actually a very easy entrance to share data in a private way, is show other similar data points and what has happened to those data points. There's a easy private way of showing that to doctors, but I don't know who's talking to AHS and telling them they can do this. It would be nice if they knew about these things. But yeah, so there are some, easy low-hanging kind of solutions that they could use to make things easier, but maybe there needs to be more communication. Yeah, maybe they need to be more open to these things. Okay, well, thank you. If you think of something later and you want to ask about it, or you have a project you're working on, you want to ask about it, feel free to contact me. I'm happy to discuss these things with you. Oh.
Sorry. Thank you. Okay, I will put up the attendance tracker again, just in case you were a little late. And I'll just make an announcement real quick. So next week, we're not going to have a lecture because it's reading week. We will post a recording, though. Dr. Wishart has agreed to do the AI infectious disease like specialty one for us recorded. So I will post that on Slack. I am not sure how exactly it's going to be recorded. So I don't know how the attendance tracking for that is going to work, but we're going to give you an option of either doing that or coming to the lecture after reading break. So the March 1st lecture. The March 1st lecture is going to be an intro to medical specialties, essentially intro to AI and medical specialties. So I would recommend doing both of them. But if you don't have time and you want to do only one, you can still do only one and grab credits for that session. More info will be on Slack as soon as I find out from Dr. Wishart how this is going to work. And if you have any questions, just DM me there as well. But otherwise, I will see all of you in 2 weeks. Thank you.